the distinct pleasure to introduce Cade Francour, coming to us straight out of Oshkosh. And he's here to talk about some research that he did working with me last summer and a smattering of other times as well. I gotta say, this year's class of seniors are kind of special to me because I'm also a senior this year. This is my 4th year at Lawrence. And so I guess I will get to do the virtual graduation with the rest of you as well. So interesting thing about Cade, I did not know it when I met him. I thought Cade was a sophomore already, but it was actually his 1st year when I met him, and that makes Cade one of the 2 students still at Lawrence that I have known the longest from a classroom type of experience. So Cade's always a great presence in class. You can look to his face on Zoom if you need a reaction for something stupid that you said, whether you said it on purpose or not. And so it's always been great to have Cade in class, and he also did great work for us as a TA in the organic labs. After this, Cade's headed down to Tejas to go to UT Austin and hook 'em horns to go pursue a PhD in, I think, inorganic chemistry, if I haven't dissuaded him from that just yet. So that's very exciting, and we wish him the best. But before that, we're all going to have the great pleasure of watching this talk. So, Cade, the floor is yours.
All right, thank you. So I'm going to be talking about my work on the synthesis of a modular luminescent radical framework that I did largely with Graham and also some now at home. So before we start, I'd just like to go over some terms so we're all on the same page, because some of these words can mean different things depending on the context. And so what is a stable luminescent organic radical? It's important you know what that is. It's basically the main point of this work. So this is an example of what one looks like. So let's start to break down the terminology. So in our context, stable means several things. One of them is that our molecule is air and water resistant. So radicals generally are very reactive because they have an unpaired electron, this little dot right here, if you can see my mouse, on the molecule. And it likes to have a buddy. Electrons like to be paired up. And so when they're not, they're going to be very reactive. And so generally, radicals in the open air react with things like water or oxygen or whatever else you may have floating around if you're in like an organic lab at Lawrence, for example. And so you want to avoid that because you want to maintain the radical nature of the molecule, at least for our purposes. Another important aspect of stability is that the molecule is non-reactive, or at least has limited interaction with itself. So one of the most immediate sources of another electron for that radical to pair up with is a copy of itself. So in the reaction solution, there's going to be multiple of these molecules floating around. And if you have those 2 radicals pair up, they're going to form a bond and again, destroy the radical nature of your molecule, that time twice as fast because you're using 2 radical molecules in that reaction. And then lastly, important for this work specifically is that these molecules are able to luminesce repeatedly. So occasionally when you have molecules that you input some energy into to get light coming out, you're going to weaken the bonds of the molecule over time, the more times you excite it, and it might eventually fall apart or degrade. And so we want ours to not do that because we're aiming to study the photophysical properties, or the way this molecule interacts with light. And if interacting with light destroys it, that sort of defeats the purpose. And so luminescent, moving on for our purposes, means emitting visible light upon excitation and ultimately relaxation. So if we have these molecules and we introduce some energy into the system, we want them to output some light that we can see. That's just for our purposes. Luminescence can mean any wavelength of light, but we want to be able to see it. Organic, as many of you may know, simply means that the molecule is made primarily of carbon. You can make these luminescent radicals with metal centers or other heavy atoms, but we're going for organic in our research. And radical, again, just means we have at least one unpaired electron in the system. And again, going forward, just so you can know what we're talking about, it's that little dot on the molecule right in that corner. So now that we are on the same page with what these things are, why do we care about them? So for one, these molecules can tell us some interesting photophysical properties about doublet state molecules. The doublet state simply means we have one unpaired electron in the system. Singlet is all of your electrons are paired up. Triplet is two unpaired electrons, etc. You can go along. This picture on the right is pretty colors and also is theoretically all of the photophysical interactions that this doublet state molecule can have, emissions, absorptions, and that sort of thing. We're not really going to get into all of those specifics, but if you do want to get into those, making this sort of model system to study them is advantageous. Additionally, these molecules are a synthetic challenge. So making a radical, as you may have garnered from my discussion before, that is able to withstand, being open to the atmosphere, repeated excitation and exposure to various wavelengths of energy, is tough. And so in order to get these molecules to last long enough for us to study them, we need to employ some clever chemistry to be able to do that. And thus, as synthetic chemists, that's exciting for us. And so that's a reason to do this research in itself. So we've talked about these concepts of stability and luminescence and stuff like that. How do we actually impart these properties into a physical molecule? So in order to protect that radical electron in the center and have it be stable to things like air and water, we need to make it bulky. So much like a kid in a overly large snowsuit is protected from the cold, and large chunky pieces to our molecule is going to protect that radical in the center from other reactive species. So the repeating hexagon, pentagon, hexagon shape on either side here may not look super impressive in this drawing, but in the real world, those are three-dimensional atoms. They take up space, and they also do this sort of propeller twist. And so the way that those atoms are arranged is actually going to physically block things like water molecules or oxygen or whatever may be in your system from actually getting at that radical in the middle, and it's sort of shielding it from the outside world, again, like a child in a snowsuit. And another important aspect of increasing the stability of these molecules is increasing the stability of the radical electron itself. So much like you want to spread your jelly on your peanut butter and jelly sandwich to the corners of the bread, you want to be able to spread out the location quantum mechanically of that radical electron to decrease the overall energy of the system. And so if we can have that radical electron exist, or be probable to exist at more points in the molecule, it's going to be more stable. And in the real world, that's achieved through the double bonds, or pi bonds, as they're also known in this system. So that allows that radical electron to basically spread itself out across more or less the entirety of this molecule, and again, increase its stability. So that's stability for our purposes. Now we're moving on to luminescence. So we want these molecules to be able to glow pretty colors when we expose them to light, and that's theoretically fine and dandy, but how do we actually achieve that? And once again, we go back to the pi bonds. So the pi bonds are doing double duty. They are both helping to delocalize that radical electron, and they also help the molecule achieve the necessary energies to absorb and emit somewhere in the ultraviolet or visible range, and that's what we want for our purposes. So generally, when you have an organic molecule like this, full of double bonds, it's going to give you that sort of absorption and emission in that it's the UV or visible. And so just so we're all on the same page with what's exactly happening when we have this luminescence, I'm going to give you a little breakdown so you know the important takeaways. So we have an electron in our system. It's at its ground state or lowest energy state, and we introduce some photon of energy. In this case, it's UV because that's what we're interested in. And the energy of that photon, again, UV in this case, is going to match the energy needed to take that electron from its lowest state to the excited state. And so we impart that photon of energy, and our electron is going to jump up to that top state. In fluorescence, which is the type of luminescence that we are interested in, that electron is then just going to fall straight back down to the ground state and emit a photon of, in this case, visible light. Due to a quantum mechanical principle that's not necessary for you to understand this work, that energy of the photon is going to be slightly less than the one you absorb. So for example, if you absorb UV, you might emit blue, which is the case on the right. So the leftmost circle is strongly emitting blue light when exposed to UV radiation. And so there's also a second subtype of luminescence called phosphorescence that we, in our purposes for this study, want to avoid. So it starts off the same, where we absorb this photon of UV light and our electron jumps up to the excited state, except in this instance, it's going to wiggle around a little bit and lose some energy to heat and vibrations and emit a lower energy, but still most likely visible photon. And so because there's this wiggling and motion of that electron involved, this process actually takes more time, but again, it emits lower energy. So if you want something that's going to glow for a long time, like a glow stick, and you don't really care about the energy, phosphorescence is perfect for you. However, if you want to gain information about the photophysical properties of these molecules at higher energies, you're going to want to do fluorescence, and that's what we're after. So we've described how you can put stability into these molecules. We've described how you get these molecules to luminesce. And the overarching aim of this study is to achieve this state of stable luminescence, patent pending. How do we actually put these two things together? So the actual work that I did in this project is that aim. So what's my inspiration is this molecule on the screen now called Kolsch's radical. It's relatively old. You might be able to see the date, and the reference is 1957. Relatively old, oldish. And it's well characterized in that lots of people know that this molecule is stable. However, for our purposes, it's boring. It's non-luminescent, at least in the visible range, and we want to have both of those properties in our molecule. We want it to be stable, and we want it to be luminescent. So I said, I'll take that and I'll make some changes. And this is what I came up with. You might be saying, that looks basically the same, except bigger. And I'll say, that's just because it's the drawing. But the actual differences are these bromines here. The introduction of these bromines into the molecule make it so that this molecule is now modular. Due to a particular reaction with palladium that I'll get into later, the introduction of these bromine sites basically allows us to put whatever we want at the locations of those bromines. So for example, if we find some molecule that's really good at luminescing in the visible range, we can attach it to that spot, and now we've combined the luminescent properties of that piece with the stable radical nature of the molecule that we have. And so just to recap, so we're all on the same page of what's actually going on with my molecule and why this is good and why you should feel good about me getting paid to do this work. So this molecule is big and bulky. It's got those chunky side pieces that are going to physically protect that radical electron in the center. It's full of pi bonds that are both going to help delocalize that spin of that radical electron. So when you have a radical in your system, you're going to increase the spin state of the molecule, and the location of that radical, each place in the molecule is where the location has the radical, it has spin density. So we're going to delocalize that spin, and those pi bonds are going to help do that. And now with the bromines, our molecule is modular. That's the big exciting input that I did. And for the synthetic chemist listening, this might interest you that this molecule is fairly easy to make. So you too can make this, and I'm not that special. So how did I exactly go about making this specifically? So at this point, I'm going to go through the actual reaction scheme of this, and just so we're on the same page with conventions. Every time I add something new to the system, that piece is going to be pink, and then where it shows up in the product is also going to be pink. So you can see what I added and where it went. And then so you can attach these cartoonish stick drawings to reality. At the bottom of each screen is going to be an actual picture of what that product looks like in real life. So where we started with this reaction, we started with that bulky side piece that we were talking about before. It is called dibromofluorine, not fluorine. Fluorine is the name of that organic molecule, and we've added those two bromines. To that, we're going to add benzaldehyde, which is the pink piece above the arrow, into methanol with a base and heat it up for a few hours. And what we're going to get out the other end is the addition of that benzene ring at the top of the molecule and the double bond that bridges the two pieces. And this really bright, pretty yellow powder, and this reaction proceeds on average about at an 80-ish% yield or so. And so we get lots of pretty yellow powder out the other end. So we're going to take that product and carry it forward, add some molecular bromine to it, and get a paler yellow powder. So when we add this bromine and stir it around in some acetic acid for a little while, those bromines are going to attach where that double bond is in that molecule and give us these two new bromines here. And for our purposes, that's one too many bromines. And so we want to get one of those off of there, which we do in our next reaction step. And very likely some of this reaction happens in the last one as well, because we're just going to keep it in acetic acid, and this time heat it up for a little while, and that bottom bromine is going to pop off, giving us back our double bond and also some hydrobromic acid as a side product, but we're already in acidic conditions, or you might say acetic conditions, and so that's not really going to be a problem. This product, shocker, is also yellow, but this one is crystalline. And so you could do cool techniques of X-ray crystallography or whatever you want, but for our interest, it's just shiny and better to look at than the other ones. So we take that nice yellow stuff and we're going to carry it forward, and we're going to attach the other piece, the other dibromofluorine, to create and finish out the skeleton of our molecule. And this reaction is a little bit different than the others. So this solvent, DMF, and our base, terbutoxide, are both air and water sensitive. So we need to do this reaction under nitrogen gas. What that does is it is heavier than all of the other components of the ambient atmosphere, and so it's going to push out all of the other pieces that might react with those things that are in the atmosphere and give you a nice clean environment in which you can do these reactions. And so we're going to add the yellow crystalline stuff from before to another piece of dibromofluorine and get the product that you see on the right. And if you kind of squint, you might say that that looks like we're done. And if you look at the bottom, it's blue, talking about blue, and the thing on the right looks like what we want, you might say we're done. Close, but not quite. If you look closely, in the place where we'd want that radical electron, we actually have a full negative charge. And that is one too many electrons. And so we're going to have to mess with our nice blue liquid and switch it up to actually get us the final radical molecule. So in order to do that, we're going to keep it under nitrogen and add this silver compound, which is going to do the nice job of stripping off one of those extra electrons and leaving us with our radical where we want it to be. And this time we get a nice, after some purification, nice orange liquid out the other end. And so this is all good in the sense that I follow directions and I should have this radical at the end. And we can do techniques like NMR or other characterization things that tell us where our carbons and our hydrogens are and how many there are, and that gives us the general structure of the molecule. But how do we actually know that that radical is there and that I'm not just telling you? Well, we do EPR. And so this is the data that we get from EPR. I made it glowy and blue because I thought it was funny. So you may be a little confused looking at this spectrum, but all you need to take away is that there is some signal. This peak and dip in the middle is indicative of the presence of a radical, which I will explain in a moment. But if there was no radical in the system, you would have no peak, and you would just have this horizontal line across the center. And so the presence of that signal is exciting, but let's get into a little bit how we actually arrive at that signal. So EPR stands for electron paramagnetic resonance, kind of like NMR, which is nuclear magnetic resonance, but for unpaired electrons in our case. And so what you saw on the last slide was the first derivative of an absorption plot there on the bottom. And so what the data that this instrument is actually taking is absorption, and the way it's presented in literature or other sources that you talk about it is as a first derivative. So what is actually giving us that absorption? So normally in molecules, your electrons can exist either spin up or spin down. And under normal circumstances, the energies of those two are degenerate, or they overlap or are the same, whatever you want to say. However, when we expose them to a magnetic field, we can actually get those two spin up and spin down states to separate from one another. By increasing the strength of the magnetic field, they'll split apart farther from one another. And the way the actual EPR instrument works is it has a constant input of some energy of photons. And if you remember from the luminescence talk, in order to bridge two states, two electronic states, you need a matchup between the energy of the photon and the energy gap of those states. So we change the magnetic field until we can get the photon to bridge those two, and we get those electrons to start moving between those states. EPR, because of the parameters of the magnet and the way that the machine works, it's usually in the microwave. So our photons that are inputting our microwave, and we get those electrons to start moving between those two states. Quantum mechanically, there's going to be a greater likelihood of those electrons being in the lower energy state, and thus a higher probability of an absorption of our electron jumping from the lower to the higher state. And so that absorption that we get is ultimately what is measured by the machine, and then we get the output as the first derivative graph, which you saw before. You don't really need to memorize all of that. There won't be a test, but the important part is that I needed to convince you that the data showed that there was a radical electron in the system, and I actually succeeded at making what I was trying to make. So we have confirmed that we have this radical. It's stable because we can do this measurements with it. We've achieved that portion. And the next thing we need to do is look at our luminescence. How are we actually going to get our molecule to be luminescent so we can achieve this nirvana-like state of stable luminescence? We need to introduce something called a chromophore. So a chromophore is just a molecule that, in our case, luminesces in the visible range. And we decided to use pyrene. Pyrene is this molecule pictured on the screen now, basically 4 benzene rings glued together. And we decided to use pyrene for a few reasons. Namely that it's cheap. So if you buy it in bulk, Costco chemistry, you can get it for less than $1 a gram. Partially this is due to the fact that it's a byproduct of fossil fuel refining. So we're taking some of that essentially garbage hydrocarbon and doing cool chemical transformations with it. And also small victory for the environment because we're taking out something that would just be pumped into the ambient atmosphere as waste and doing cool, useful science with it. But most importantly, at least for our context, not to diss the environment, is that it's well known to luminesce in the visible range. So pyrene is used in certain dye molecules. It's used as a sensor for solvent systems. It luminesces different colors depending which solvent that it's in. But also we just had some lying around for a different project, and so we decided to why not try and tack it on. But how exactly are we going to get this chromophore molecule to attach to the radical molecule that we've created? Well, I hinted at it before, but the introduction of those bromines allows us to do cool palladium chemistry and combine the functionalities of those two molecules. So what is exactly that palladium doing? don't be alarmed. This is a overwhelming slide, but I'll break it down for you piece by piece, and we'll figure it out together. So for starters, this is a clockwise cycle. So it's going to start at the top and go around clockwise. Don't be alarmed that this clip art clock only goes to 10. I'm not sure why that even exists, but you get the idea. So you're going to start at the palladium 0 at the top and work your way around. It's a catalytic cycle, so it keeps going. And then the other helpful convention that I've added is that the radical molecule is symbolized as the red R as you go around, and the chromophore is a blue C. Red for radical, and the C is blue because we want it to be blue. I put a lot of thought into that. So the three major pieces of this catalytic cycle that we're going to talk about are oxidative insertion, transmetallation, and reductive elimination. So I will get into oxidative insertion. So once you introduce the palladium into our system, we have the radical molecule that has those bromines on it that we added for this project. And the palladium is going to sort of wiggle itself in between the radical molecule and that bromine and wedge itself into that bond. In that process, the oxidative portion of oxidative insertion, it's going to go from palladium 0 to palladium 2, increasing its oxidation state. The next step is sort of the neatest part of this catalytic cycle, and the reason why everybody likes using it is this transmetallation. So the first sub-step of this step is that we're going to activate with a base. So some base in our reaction system is going to come in and swap with the bromine that was bonded to the palladium, getting us this compound on the bottom, the radical, palladium, and base all hooked up together. And then the actual transmetallation step is where our chromophore down in this corner, bonded to a boron, is going to do a switcheroo with the base on the palladium. And after that step, the radical and the chromophore are both going to be bonded to the palladium, and the base is going to be switched on to the boron. Here, the boron is acting as the other metal in the transmetallation. It's not really a metal, but it's acting as one. And in other scenarios where you have this palladium catalysis, you can use things like tin or zinc. Those are actual metals. But this specific palladium reaction, called Suzuki coupling, uses boron because the others are kind of toxic. Tin stuff isn't good for you. And also this works really well. It's robust to a lot of conditions. And so Suzuki coupling is what we decided to use. But in any case, the important takeaway is that after this transmetallation step, we now have our radical, our palladium, and our chromophore all connected, setting us up for reductive elimination. So the final step of this catalytic cycle is that the palladium is going to pop itself out of that bond and go from palladium 2 to palladium 0, hence the reductive elimination, leaving us with this nice, crisp new bond between the radical and the chromophore. And so when the palladium pops out, we have a new bond formed between the radical and the chromophore, combining those two functionalities finally into one. So this is a lot, but what are the main things you need to know from this catalytic cycle? So we can take our chromophore bonded to the boron and our radical with the bromines all over it, put it in a pot with some palladium, and out the other end we get this hulking monstrosity of a bunch of hexagons where instead of those bromines we now have those pyrines, and hopefully we've combined the functionalities of our stable radical portion and the luminescence of the pyrene. And in this case, I've just depicted it with 2 pyrines on one side of the molecule. If we tried to add 2 to the other side, it would get really big and characterization would be tough. So we decided to go with that for the purpose of this work. But by using this palladium catalyst, we're able to combine these 2 things together. And after that, you may have a question or several questions. That's your prerogative. But the one main question that I'm going to focus on is how do we actually get this pyrene to have this boron piece on it so we can actually do this coupling reaction. So how did I go about making the pyrene into the coupling partner for the radical? So we start off using this fun looking molecule called N-bromosuccinimide, or NBS, which is essentially just going to tack a bromine onto our pyrene in that position there. And again, just stirring in solvent at room temperature for a little while works real nicely. And we get these ugly brown crystals out the other end, but high yield, so I don't want to call them too ugly because they worked well for us. So after that step, we're going to take our newly brominated pyrene, and this is where we actually want to attach the boron compound. And my initial try was to use a prep from a paper that called for a different palladium reaction. But after lots of struggling, trying to come up with appropriate glassware setups and weird workup conditions with distillation of toluene and water and high temperatures and not fun, the best I could do was get the starting material back out. And so I decided to nix that route and try to go somewhere else. Unfortunately, due to current world events, I wasn't able to actually pursue this in the lab any further, but I did find a paper that suggested an alternative method of attaching that boron, which essentially is going to turn this brominated pyrene into a Grignard reagent, in which you have this magnesium metal wiggle itself into the bond between the pyrene and the bromine, and then attack the boron compound there. And through some interesting complexation with magnesium, the hydride is going to be our leaving group. And essentially, what we're going to get out the other end is this molecule on the right that is hopefully our pyrene with our boron compound on it that can do our Suzuki coupling. But that is going to be for whoever picks up this project next and can actually do it in the lab. Best of luck to them. So after we do that, what are our next steps synthetically? I propose the idea that instead of trying to make the entire radical framework with all of the bromines attached and then put the chromophore on there, I suggest we just add that right away in the beginning. So we're going to couple the dibromofluorine to the pyrenes and get two on either side, and then do all of the synthetic transformations that I highlighted before to end up with our combined radical and chromophore molecule there on the right. Another question that I have that you may have not thought about until now, that's why I put in italics for emphasis, is what are the next steps computationally? So while not in lab, I've been at home on the computer lab doing some calculations that take a really long time with density functional theory, but are very rewarding out the other end when you get results. So one of those is geometry optimization. So there's a lot of electronic repulsion in these molecules. They're weird shapes and they bump into each other in three-dimensional space. And so this is a DFT calculated geometric optimization of the molecule with the two pyrenes attached. So in the plane of the screen is the dibromofluorine that has the two pyrenes attached. And you can see on the top, the other bulky side piece and the benzene are doing that sort of twist to get out of each other's way, which also helps to block that radical electron from interacting with other things. And the pyrenes are sort of both tilted forward again to lower the overall energy of the molecule. Just FYI, this DFT calculation took 50-something hours on my Dell laptop at home. Not quite a supercomputer, but it's doing its best. I was also able to do a spin density plot that finished calculating this morning. And so I was able to, after watching some foreign language YouTube videos and messing around with other downloaded visualization software, to actually get a plot that shows where that radical electron is actually spread out across the molecule. So basically everywhere you see that red is where some of that radical electron is going to quantum mechanically exist. And as you can see, it's basically spread out over the entirety of that radical framework, but it doesn't go onto the pyrenes. And that is theoretically going to help those luminesce better and also maintain the non-reactivity of the radical electron in the center. So we're combining the two functionalities of the pieces, but they're not really mixing, which is to the benefit of both of them. And so for this work in general, what does the future hold? Because this is now modular, we can take essentially any chromophore we want. These are examples of some laser dyes that emit very strongly in the visible range, lots of pretty colors. And so we can attach them in various combinations or try to get different colors to come out of these molecules in whatever fashion we want. And we could also do crazy things like try and link multiple radical frameworks together by a chromophore and do like a luminescent polymer. The fun is endless. But another more immediate future investigative route is that we can do more computation. So density functional theory can also be used to estimate the energy gap between the ground and excited states of this molecule. So while I'm not actually able to make it in the real world lab, I can make it on a computer. And if you remember from the luminescence talk before, the gap between our ground and excited states is roughly equivalent to the energy of the photon that we need to bridge them. And so what that means is computationally, we can tell if this molecule will luminesce in the visible range or not, which can then later go on to be confirmed in the lab, ideally. And thinking about those two things semi-recently, as in when I was making this presentation, if we can attach whatever we want, we can also do this computation to tell if these will emit visibly or not. This is sort of a roadmap for computation-driven synthesis. So instead of trying to make these things first and then sort of guessing whether they'll luminesce visibly or not, we can theoretically calculate whether they will or not on a computer and see which of these molecules will be best to luminesce in real life, and then somebody can go make them in a lab so we can actually observe them and study how they behave. And I think that is a cool route that could potentially go into the future with this now modular radical framework. So for this work, I'd like to acknowledge Graham Sazama, my research advisor, Deanna Donahue, who's my academic advisor, and the two of them for putting on the capstone class. My peers and friends, many of whom attended today, thank you, who have taken this chemistry journey with me. All of my lab mates from the summer and during the year who helped with this work and answered questions and whatnot. Stockroom people, D. Martin, all those that work for him for providing reagents and glassware and love and affection. The ACS Petroleum Research Fund, which paid me to do this work. My parents, who I'd literally not be here if they hadn't decided to let me be here. And my dog, Barry. So at this time, I'd like to take any questions you may have, and I thank you for listening.
So let's give Cade a round of applause. I'm so awkward. Yay! And I will open up the floor for questions. Feel free to just unmute yourself, or if you feel more comfortable to raise your hand or send me a chat, either of these ways. I think Allison Fleshman has a question.
She looks very excited about her question.
I can wait. I'll let other people ask first.
Go ahead, Allison. I don't see anything else.
Go team. Okay, fun stuff. I may have missed this at the beginning. Sorry, there's other emails I was kind of finishing up. So what's the ultimate goal or application for these molecules?
So long term, this is definitely a long-term route to actual application to the real world. But you could do like screen technology, so like organic molecule, like OLEDs or organic light emitting diodes. So you can do something like that with these, but you'd have to greatly increase their luminescence lifetimes. But something like that, essentially, so technology. But definitely at the moment, these are basic science interests as opposed to actual application. But
I'm
they're still
all in
really
the business
cool.
of fundamental versus actual applications. Okay, so that leads me to my next question. So when you've attached the chromophore to the side, or you've stabilized the two chromophores on each end, is there any possibility that you could stabilize it with different chromophores, extending the range of light that can be absorbed, accessing different types or multiple types of electron transfer into the higher states?
So that's definitely a possibility. Now that it's modular, you'd have to probably, if you wanted to attach different ones to either side, protect one side in some fashion or another. But it's definitely a possibility. and would be absolutely an interesting avenue of investigation for the future. But yeah, I think so.
Cool. Follow-up question to that, unless anyone else has a question. Back in the day, I don't remember, it's been years ago now, the goal for some, at least solar cell technology or solar cell implementation of these types of go team, just hang on, was to use use molecules to get to where you could get one photon to excite multiple electrons. And this is probably a naive question when it comes to radicals. But if you already have a radical, is it possible to get that radical to then get excited to a higher energy state and then have that state that's now empty of the radical be then occupied, causing internal electrons to then, like a cascade effect of excitation? I'm gonna move my camera to Graham to see his face.
I was gonna say that my best answer to that would be strictly speculation. So you may.
I'm curious your speculation. This is just now shooting from the hip.
I mean,
like,
my speculation
cool.
would be I don't know, and that would be cool. But maybe Graham has a better answer. I don't really know.
I mean, people are chasing those kinds of systems. They do exist. There's a little bit of the major question is usually, do you have enough photon flux to catch a second photon before relaxing down into the ground state?
Mm-hmm.
So given that Cade was telling us that fluorescence is most likely, that process tends to be very fast, on the order of, nanoseconds or so. And so you need either high flux laser to do 2 photon absorption or something along those lines. But it's certainly not impossible.
I'm talking about 1 photon, multiple electron excitation from a single photon, because your phosphorescence is avoided.
We will have to talk more about this.
Cool.
I have not heard that. I don't know how that works.
Go team. No, it's really cool. Just the fact that you've got the 2 chromophores showing that you've got the electron density in the center and it's not going to the sides. That was really cool. So, good job.
Thanks.
Other questions? Don't be shy.
Yes, D-Mart.
Could you go back a few slides to your what's next
Sure.
steps, or the synthetic ones?
This one?
Yes.
Okay.
Is there any concern that by doing this first, you're going to start getting additions in places that you don't want during the bromination steps?
So that is possible. However, I think that those side products would be significantly less likely because those the reactions where we have the bromination of the pyrene, those occur at the spots where it's now bonded to that radical piece. And so you might get some on either side, but that addition wouldn't necessarily hamper how it would behave. It might actually increase the phosphorescence chance due to the heavy atom effect, but it might also be such a negligible side product that we wouldn't necessarily have to worry about it. That is a possibility to think about, but I think that this is perhaps the easier or higher yield route to go as opposed to making the radical first.
Okay.
Any other questions?
Could you
Aiden.
go back
Oh, sorry.
Oh,
Go
Adam
ahead.
can go. Adam can go.
Okay. Could you go back to the slide where you brominated the pyrene? I'm just wondering do you have any insight on the selectivity of this reaction or why it chooses to brominate at that location? And you said in pretty good yield too.
Yeah, so I don't necessarily know why it's that spot. I'd have to assume that it's because of it'd be some sort of resonance structure of the intermediate. But it is definitely just either there or obviously at the same spot on the other side. But when it's actually doing the reaction, those are the same. It's not the end-on ones, because that's what I initially thought was happening, because when I initially found this prep, it was in one of my SciFinder free patent articles that was in Korean that I Google translated. and it did a decent enough job of telling me the prep, but it didn't translate any like NMR or anything like that. And so when I actually when I was trying to find a theoretical NMR to match up with it, I found a different prep and used that, and it just indicated that it was that product that forms. And so when I made my theoretical NMR on one of the sites where you can build the molecule and it tells you what it'll look like, it wasn't matching up with what I was getting because I was putting it on the end, and that wasn't what was actually happening. But when I switched it to the spot that it's in now, it matched up. And so I'm not really sure why it does that selectivity 100%, but that's what it does.
I guess
Okay.
Aiden now.
Yeah. Is this size of the chromophore proportional to your fluorescence intensity? Meaning, is the more pi bonds you have, you're going to fluoresce more because you can absorb more?
I don't know about more or less, but the relative energies of those interactions are going to be different based on how extended your pi system is, or if you have heteroatoms in there. I'm definitely not confident in saying that it's going to be any more or less. I don't really think it would be. I just think it's going to change the relative energies that you're dealing with.
I feel compelled to chime in here. So Cade has that exactly right. The more pi bonds you have in conjugation, the smaller the homolumo gap, and so the longer the wavelength. The way you increase the amount of fluorescence is by making the molecule more structurally rigid, generally speaking. So sort of, because in this case, it's a pretty rigid structure being that flat aromatic system, but it in and of itself, without you have to have fewer vibrations available to the molecule to have more fluorescence.
There you go. Yes, Alice.
Question. So just because I have some quantum students in the room, is there,
Oh,
so
boy.
aside from, no, it's okay. Aside from doing computational, so
We lost you, I think.
Yeah, you muted yourself.
Are you still there, Allison?
Still muted. There we go. Okay.
can't touch buttons.
Yep.
Instead of doing DFT or density functional theory calculations, I've learned to say it that way. Is it possible to model this system when you've got the two chromophores and the thing in the middle with either particle in a box or some sort of augmented simple model so that you can get a quick idea of the delta E of the homolumo gap?
I mean, it's probably possible. I don't know. These computational techniques are all very new to me, so I don't know how to part them from one another, but I assume that that's possible. But I don't have a definitive answer for you.
Cool. Well, I was just like, so looking at it, so you said that, so if you think about the particle in a box, for like if the radical's in the center, and then depending on how far out your bromines are, so if you, like you said, you can attach anything to those bromine locations. If you attached, say, like 2 or 3 more conjugated systems that didn't block it, that did extend it out, your box would be bigger, so your delta would be smaller. So you could almost do like a back of the envelope calculate. I'm not saying do any sort of,
yeah.
Because you said it was 56 hours to define the spin state. That's insane.
Well, that was combined with geometry, so that was, I was doing both of those things, and with a really good basis set that Graham told me to do.
Always use a crappy one first.
Well, I did those. Those were like 3 hours, and then this one was much longer.
Anyway, I'm just curious because if you can find a good model that way, you can almost like inform your DFT before you do them. But
yeah, that's definitely possible. I'd be curious too to see what kind of systems you'd have to introduce to get them to actually spread out that spin density more, and what the difference between the ones that confine it versus the ones that extend it are.
Right.
So that would
and just to have a quick and dirty calculation that you can kind of just approximate before you do the work to see if it's even worth the time.
So organic chemists have made it even simpler than that, and to avoid any quantum mechanics at all, you can just count the number of double bonds and somewhat reasonably predict the wavelength of calculation, like plus or minus, or the wavelength of fluorescence or minus 10 nanometers, just by adding up the number of double bonds in conjugation and then multiplying by some factor. So, I mean,
Which is a beautiful particle in a box model.
that's right. That's right.
Go team.
Any other questions?
Yes, Evan.
I was just curious. So you were talking about how with the spin density, we don't see any spin density extend onto the chromophores. And I was wondering if you could talk a little more about why we don't want the spin density to extend onto the chromophores, or why that's important. Because it seems to me if we wanted an interaction between the chromophores and like the base molecule, we would want to see that radical spin density or some type of interaction of the radical on the chromophores.
So that's a really good question, and that is one that I think I'm going to deflect to Graham, because that was just an offhand comment that he made to me in one of our meetings about when I told him I was going to try and calculate the spin density. So I don't really know why that helps or not. So I'm taking him in.
Sure. Yeah. No, we don't really know whether it helps or not. I guess that's kind of the key. We want to study that exactly. So knowing where it is the key to figuring out where it needs to be on whether it luminesces or not. And this is an interesting one to compare to some of the other radicals that have been made in my group. So I think Mick will be talking about that later this month. His molecule may have more or less spin density on the chromophore portion. And so we can just look at whether the radical being localized on the chromophore or not has any effect on its photophysics. That's when the problem gets really interesting, when you can make those comparisons.
Okay. Well, feel free to stay if you have further questions, but I'm trying to be cognizant of time. So I want to thank Cade once again. And so a round of applause or a thumbs up. Thank you so much, Cade.
Thank you, everybody.
Feel free to hang around for a moment if you have another question. The meeting will be open, and otherwise, thank you for joining us. And if you're in 680, I did get you logged. Thank you so much. And we will see you at the next talk, which is 4 o'clock on Monday, and it is going to be given by Aiden.